discuss about Gauss Divergence Theorem in this lecture. If V is the volume bounded by a closed surface S and F is vector point function with continuous derivative in V, then double integral S F dot n ds is equal to triple integral V over volume del dot F dV, where n is the outward drawn normal unit vector to surface S. So now let us suppose F is equal to F1i plus F2j plus F3k be the vector. Then from left hand side double integral S F dot n ds is equal to double integral S F1i plus F2j plus F3k dot n ds. This is left hand side, and we have to prove left hand side is equal to right hand side, and our right hand side is triple integral V del dot F dV. dV is over volume integral and F is F1i plus F2j plus F3k. So del dot F is equal to del of del x I plus del of del y j plus del of del z k dot F, and this gives us del F1 over del x plus del F2 over del y plus del F2 over del z. So right hand side is equal to triple integral volume del F1 over del x, del F2 over del y, del F3 over del z dV. So we have to prove left hand side is equal to right hand side. First we take the part triple integral V del F3 over del z dV, where V is the volume integral. So we take this as triple integral V del F3 over del z dx dy dz. So this is volume integral over integral dx dy dz. Now first we consider the surface. Let's suppose S be the any surface, and we divide suppose this into two parts, surface S1 and surface S2. Let S1 is the surface, Z is equal to F1 xy, and S2 is the surface, Z is equal to F2 xy. So this is lower surface and this one is upper surface, and let us suppose its projection in xy plane is R. Now this volume integral is equal to double integral R, where S1 is the lower surface, that is Z is equal to F1 xy, S2 is the upper surface, that is Z is equal to F2 xy. So we can write this as R. Z1 is F1 xy and upper surface is F2 xy del F3 over del Z dz dx dy. So when we integrate this part, integration, because this is derivative, partial derivative with respect to z and integrating with respect to z, so this gives us F3 x comma y comma z, because F1, F2, F3 these are functions of x, y, z, and z is from F1 xy to F2 xy dx dy. This one is equal to double integral R F3 x comma y comma F2 x comma y minus f3x comma y comma f1x comma y dx dy. Now we are in double integral and we have to write this in the form of left hand side, that is double integral f1i plus f2j plus f3. It means for f3 we must get f3k dot n ds. And in last problems we have discussed that ds, when we take the projection in xy plane, that is dx dy over n dot k. What is k? It is the outward in the direction k, and is the outward drawn normal to the surface. So similarly in this case we take for surface S2 dy dx as k dot n2 ds2, because where n2 is the outward drawn normal to the surface. n2 is the outward drawn normal to the surface and n1 is the normal for S1 surface. Let us suppose n2 is the normal for S2 surface. So similarly as for S1 surface we get dy dx is equal to minus k dot n1 ds1. Why minus in negative in S1 case and positive in S2 case? Because we have to take the outward drawn normal to the surface, and this normal n1 is along negative direction of z, or we can say this makes an angle which is more than 180 with the z-axis. So we take for this surface negative because outward drawn normal, and for S2 surface we take the positive side, that is dy dx is equal to k dot n2 ds2. So f3 for S2 surface we have dy dx is equal to k n dot n2 ds2, and for S1 surface minus k dot n1 ds. So from this we get double integral r f3 dx dy for this one is for S2 surface minus f3 dx dy, this one is for S1 surface, and for S2 surface dy dx is equal to k dot n1. So this one is equal to double integral r f3 k dot n2 ds2 minus negative, and dy dx for S1 surface is minus k S1. So negative becomes positive, f3 k dot n1 ds1. So by adding this we get f3 k dot n, where n is the total normal, and when the surface S was divided into two parts, S1 and S2. So this we get for this part, del f3 over del z dv is equal to f3 k dot n ds, and we have to similarly we can prove, which you can see we have proved this part, that double integral f3 k dot n ds is equal to double integral f3 k dot n ds. Similarly when we solve the volume del f1 over del x dv, you will get double integral over r or surface f1. So here you have z and we got k vector, for x we get I dot n ds, and this is the surface integral. And similarly for case f2 over y dv, you will get S F2 J dot N ds. By adding the 3 on left hand side and adding the 3 on right hand side, you will get the proof of the theorem. This is first part. Second part, if you have the surfaces, many surfaces, then we first divide the surface by drawing parallel lines. And now if we find the surface integral, when we start from here, the surface integral from this side again by this side. So similarly, as when we draw the parallel lines to divide the surface, then this integration gets cancelled, because we know that integration from a to b f dx is negative of integration from b to a f dx. By this property, the integration along the straight lines in opposite direction gets cancelled, similarly as we get in this side. So when we add up all integrals, the integration along these straight lines gets cancelled because of opposite direction, and when you add by removing this, we get the total surface S. So this was the extension of a surface when surface is not one but it is of many parts. So next we do an important example of this question. Example: use divergence theorem, find A dot ds over surface S, where A is the 4xi minus 2y square j plus z square k, and S is the surface given by x square plus y square is equal to 4 between z is equal to 0 to z is equal to 3. So by Gauss divergence theorem, we know that double integral S A dot ds, we can write this as in surface integral definition A dot n ds, and by the above theorem, this one is equal to triple integral del dot A dv. So what is A? A is here 4xi minus 2y square j plus z square k. So first we find del dot A, that is when you solve this, you get 4 minus 4y plus 2z. So again this is equal to triple integral 4 minus 4y plus 2z and dx dy dz. Now here the surface is z varies from 0 to 3, and we can change the x square plus y square is equal to 4 in polar coordinates, or you can solve this either by another way. So this you know about how to solve the double integral, triple integral. So by solving this, you will get the value of the surface integral. Thank you.